Today we didn't get a chance to finish a couple of examples because, of course, I had to pick more examples than we had time for. So where we're going to finish off the material for today was with these last two examples on complex fractions and finding their limits. Well, one's complex and one just we have to put together with a common denominator in order to find our limit directly. And then I want to look at another example of a piecewise function that's very similar to one of the ones we looked at together at the beginning of section 2.2. But there were a couple of questions on that on the homework that I wanted to make sure that we really understood what those look like. So let's start with example C from the indeterminate limits example 2.3.4. So for this one, we wanted to find the limit as x approaches 1 of 1 over x plus 1 minus 1/2 divided by x minus 1. So when we end up plugging in with direct substitution, we get 1 over 1 plus 1 minus 1/2 all over 1 minus 1. So we get 1/2 minus 1/2 over 0. So we get 0 over 0. Once again, not good, sad face. So we have to come up with another method to solve this problem. So let's try taking the limit as x goes to 1. And now let's look at these as two different fractions. 1 over x plus 1 minus 1/2 divided by x minus 1. And so we'll carry through our limit. The limit as x goes to 1. Let's put the first fraction over a common denominator. So each will have to have 2 and each will have to have x plus 1. The first fraction does not have the 2, so it will have a 2 times 1 over 2 times x plus 1. The second one has the 2, but it does not have the x plus 1, so it'll have 1 times x plus 1 all over the 2 times x plus 1. And that's still just divided by x minus 1. And I'm writing out all the steps for you here. If you see them a lot faster, you can certainly write them out in a more succinct fashion, but I'm showing all of the steps for anyone who might need them. So if we look at it, the limit as x approaches 1, now we have 2 minus, in parentheses, x plus 1, because all those 1's can be implied, all over 2 times x plus 1. And we're going to divide it by x minus 1. So we're getting closer to being able to evaluate this directly. So our limit as x approaches 1 then is going to be of 2 minus x minus 1. And 2 minus 1 is 1, so we get 1 minus x over 2 times x plus 1. And we're going to divide that by x minus 1. So with division of fractions, or let's see, carry our limit through. And with division of fractions, that means we're really going to have 1 minus x over 2 times x plus 1. And we're going to keep that one. We're going to switch the sign to addition or to multiplication from division. And we're going to flip the 1 or the x minus 1 over 1 to 1 over x minus 1, and then we can multiply through. So we really get a limit of x as x goes to 1 of 1 minus x over 2 times x plus 1 times x minus 1. And you might notice that we have an x minus 1 in the denominator and a 1 minus x in the numerator. If we pull out a negative from the 1 minus x in the numerator, we can make it a negative 1 times x minus 1. We can switch it around. And now when we divide by 2 and x plus 1 and x minus 1, now that magic that we were looking for that will help us be able to do direct substitution happens. We have an x minus 1 over an x minus 1, so we can reduce those out. And now we're just left with the limit as x approaches 1 of negative 1 over 2 times x plus 1. And now we can just simply plug in the 1. So we get negative 1 over 2 times 1 plus 1, which is 2, or a negative 1/4. Example D is similar to example C in that we need to find a common denominator so that we can combine our fractions and see if we have a factor that cancels on both the top and the bottom, so in the numerator and the denominator, so that we can then use direct substitution. So let's see, we'll carry our limit through, right? The limit as x goes to 3. And now we're going to have 1 over x minus 3, and we've got 4 over x squared minus 2x minus 3. So let's make this 1 over x minus 3 minus 4 over, and let's factor. Well, multiplies to give me negative 3, and adds to give me negative 2. Well, that would be x minus 3 and x plus 1. So this makes our common denominator a little bit easier because both of them already have an x minus 3. So the first fraction is only going to need the x plus 1. So now we have our limit as x approaches 3 of 1 times x plus 1, and then minus our 4, all over our common denominator of x minus 3 and x plus 1. And the 4 doesn't need to be multiplied by anything because it already has both factors of the common denominator. So now if we simplify, we get our limit as x approaches 3 of x plus 1 minus 4 is going to give us x minus 3. And in our denominator, we also have an x minus 3 and an x plus 1. So that little bit of magic that we found on the last example comes back here because now we can reduce out the x minus 3 in the numerator and the denominator, and we are left with the limit as x approaches 3 of 1 over x plus 1, which then in turn will say we can do direct substitution. So we make it 1 over 3 plus 1, which is 1 over 4. For the last example in this section, it's actually a lot easier if we just graph it because we were given a piecewise defined function where we have f of x equals 4x minus 3 if x is less than 2, or we have x minus 3 quantity squared if x is greater than or equal to 2. So let's graph this function. So first off, we're going to need a set of axes. Oh, I guess mine are going to be red. And then we're going to, we have our x, let's get our y in there. All right, so now let's put our functions on this graph. So I guess since I drew the axes in red, I'll put the graph in black. So we say that for 4x minus 3 is our line if we have x less than 2. So the question is, what happens at 2? When x is 2, I get 4 times 2 is 8. 8 minus 3 is 5. So it's up at 1, 2, 3, 4, 5. It is not equal here, so we will have an open circle. And then we're going to have a line leaving from here that goes through our x-axis and down through our y-axis as well, right? It has a positive slope, right? We can see that because it is positive 4x minus 3. It's going to go through negative 3 down here, right? 1, 2, 3. Suppose I didn't keep my scale exactly the same. And then after x is 2, anything greater than or equal to 2 is going to be x minus 3 quantity squared. Well, when x is 2, when it's equal to 2, we get 2 minus 3, which is negative 1 squared, which is 1. So it starts here, and then we have a quadratic that at 3 comes down and touches our axis and then goes on off to infinity. So the question is, can we find both one-sided limits and the two-sided limit for this piecewise function? So if we examine the limit as x approaches 2 from the left, as we get closer and closer to 2, we get closer and closer to 5. Which we could also find if we hadn't graphed it by looking at, as x goes to 2 from the left, it's going to be where x is less than 2. We could also say that this is the limit as x approaches 2 from the left. And in this case, the f of x that we will be looking at is the 4x minus 3. So we can see that here we have a polynomial, so yes, we can use direct substitution. So we would just get 4 times 2 minus 3, so 8 minus 3, which is 5. So our graphical approach and our analytic approach arrived at the same answer. So what happens when we go from the right? Well, if we look at our graph, as we get closer and closer from the right, we end up at y equals 1. So we would have 1 graphically. But if we looked at it analytically, our limit as x goes to 2 from the right means that the values are greater than 2 and coming back to 2. Well, when x is greater than 2, we have to use our function of x minus 3 quantity squared. Once again, it's a polynomial, so we can do direct substitution. So we'd have 2 minus 3 quantity squared, which is negative 1 squared, which equals 1. So once again, our graphical and analytic solutions definitely agree. But now the real question is, does the limit exist? Well, remember back to our limit definition. In order for the limit as x approaches 2 of f of x to exist, the limit from the left has to equal the limit from the right. So we would say here, graphically, we can see there's a jump in it. They're not connected. They don't approach the same value. So we would say does not exist. And that would be true. We would claim the same thing analytically because we would say it does not exist because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. The last topic we need to cover in this section that we didn't have time to get to was the squeeze theorem. I'm going to go over it with you here in the video a little bit, but I'm also going to answer some questions and go over the last example with you guys again on Monday. There are some homework problems in WebWork 2 that do use the squeeze theorem, so I want to make sure that we get a chance to look at it over the weekend and spend some time with it. So what does the squeeze theorem say? How do we know what is happening? So we're going to start with thinking about the problem like this. I said if I have a function g of x with the following property that 2x minus 1 is less than or equal to g of x, and g of x is then also less than or equal to x squared plus 2x, minus 2x plus 3, then what do you think the limit as x approaches 2 of g of x is? Well, we know that it's stuck between this line and this quadratic as x gets closer to 2. So let's see what the limit of each of those is. Let's find the limit as x approaches 2 of 2x minus 1. Well, that's a polynomial, right? It's a line. We can just use direct substitution. Well, that would be 2 times 2 minus 1, or it's 3. Okay, and on the other side, what is the limit as x approaches 2 of our quadratic, which again is a polynomial, so we can use direct substitution. We get 2 squared minus 2 times 2 plus 3, which gives us 4 minus 4 plus 3, which also gives us 0 plus 3 is 3. So the limit of the function that is below or equal to g of x is 3. And the limit for the function that is above or equal to g of x is also 3. So what do you think that implies about the limit of g of x, which would be stuck in the middle here? So what is our limit as x approaches 2 of g of x? Well, I'm thinking that that limit is probably between, 3 and 3 would be my guess here. I'm thinking that 3 is going to be less than or equal to our limit as x approaches 2 of g of x, which I think is going to be less than or equal to our limit on the right here was 3, the higher one. So what numbers between, say, 3 and 3? Hopefully you said it's still 3, because there is no number between 3 and 3, but they do have equals. So we're going to say that we think that our limit as x approaches 2 of g of x has to be also 3. This is the idea behind the squeeze theorem. So that limit can be found because we have two other functions at the same value of x that are squeezing it into being the exact same value that they are. So here, it has to be 3. So let's look at what the squeeze theorem tells us exactly. So the squeeze theorem formalizes this idea that we've stumbled upon by saying if we let f of x, g of x, and h of x be 3 different functions that are defined for all x not equal to a over some open interval that contains a, and then if we say that g of x is between f and h, so f of x is less than or equal to g of x is less than or equal to h of x, for all x that are not a in that open interval that contains a, and if we also say that the limit of, as x goes to a, of f of x is the same as the limit of x goes, as x goes to a of h of x. So think the lower and the upper bounds of g of x have the same limit, L, where L is a real number, then we're saying that the squeeze theorem here tells us that the limit as x goes to a of g of x has to also be L. We saw what that looks like on the example before this. If I am bounded by 3 on both sides, then my value can only be 3. What does that look like if we examine another kind of problem that's a little bit different than the simple one I gave you before with polynomials? I brought in some trig. I know, not your favorite, but I promise it will be okay. So I said, let's use the squeeze theorem to evaluate the limit as theta goes to 0 of theta squared times the sine of 1 over theta. Well, we can see already that 0 squared times does not exist, right? Because you can't do 1 divided by 0. So that's not exactly going to work, because if we use our limit laws here, we end up with the limit as theta goes to 0 of theta squared times the limit as theta goes to 0 of the sine of 1 over theta. So while this one is going, the first will go to 0, right? The second one does not exist. So this is a problem. But how can the squeeze theorem help us here? Okay, well, let's think about it this way. What values can sine take on? Sine, the sine of 1 over theta, vacillates between -1 and 1, right? We're not increasing the amplitude of sine here by multiplying by any constant in the front, so it's just 1. So our amplitude from sine goes from -1 to 1. Okay, so sine is between -1 and 1 for all values of theta. Okay, so what happens now if I include our theta squared? I multiply it by this concept. Let's see here what happens. If I take a theta squared and multiply it, I get negative theta squared then, must be less than or equal to theta squared times sine of 1 over theta, which must be less than or equal to 1 times theta squared, which would be theta squared. for all values, values of theta, not equal to 0. I forgot to say that on the other one. Not equal to 0. So that would be true, right? But here's the thing. If we take our limit here, like we did in the previous example, we would say our left-hand limit here would be the limit as theta goes to 0 of negative theta squared would equal 0, right? Because it would be negative 0 squared. Well, negative 0 squared is the same as 0. If we look at our right-hand side, we would say then that the limit as theta goes to 0 of just plain old theta squared is going to be 0 squared. Again, another polynomial, so it's 0. What that means then is that our limit for theta squared sine of 1 over theta has to be between 0 and 0. So we have 0 is less than or equal to our limit as theta goes to 0 of theta squared sine of 1 over theta, which is less than or equal to 0. So if our limit has to be between 0 and 0, well, it can only be 0. So therefore our limit as theta goes to 0 of theta squared sine of 1 over theta is going to equal 0. And this is by the squeeze theorem. Right? By the squeeze theorem. So it's a little bit of an abstraction, but I think we can get there. Do you think that our result would be different if we change g of x to theta squared cosine of 1 over theta and still find the limit as theta approaches 0? If you think about the amplitude again of cosine, you'll know the answer is no, that it's still 0. So we would end up having here, we would have again negative 1 being less than or equal to cosine of 1 over theta, which would then also still be less than or equal to 1 for all theta, for all values of theta not equal to 0. And then if we multiply the entire inequality by theta squared, we'd get negative theta squared then is less than or equal to theta squared cosine of 1 over theta, which is less than or equal to theta squared. For all values of theta not equal to 0. And then again, our limit as theta approaches 0 of negative theta squared is going to equal 0, which is our limit as theta approaches 0 of regular theta squared. So we now have then that 0 is less than or equal to the limit as theta approaches 0 of theta squared cosine of 1 over theta, which is less than or equal to 0. And therefore, by our squeeze theorem, right, by the squeeze theorem, there we go. Let me scooch this up so I can finish writing. Then we know that the limit as theta approaches 0 of theta squared cosine of 1 over theta is also 0. So we'll go over these squeeze theorem problems again in class on Monday, and remind me if I forget, I will show you what the graphs look like. They actually look really fascinating. You find out that once you look at each of these as they approach 0, their graphs go like this, and they kind of come in and settle into 0 and then take off again. And both of them do it. It's really, really fascinating. So I'll pull it up on Desmos and show you on Monday in class.